It's actually really interesting. So one of the reasons why there is a huge global push towards 5G is also because it increases the capability of something like V2X. 5G promises speeds of about 100 Gbps, which is significantly more. I'm sorry, it's promises 20 Gbps, which is significantly more than what 4G can do, and something that most auto manufacturers and governments feel is capable of supporting all the information that they spoke about in the previous video. I mean, just the constant transmission of data, it really adds up. It might not feel like a lot, just sending binary codes of whether you're braking or accelerating, but keeping track, logging all of that data over a lot of time, uses a lot of bandwidth. So yeah, that's one of the reasons why 5G is being pushed a lot by automakers. You'd be surprised to know. That video is actually slightly old. A lot of that information is now public. You'll find research papers online. The US government and specifically the US military really does push all of these technologies a lot here in the US, and that really then spreads all over the world. I'm sure some of you know, but the others might be surprised to know that the initial autonomous vehicle push globally was started by the US military. It was the DARPA challenge, which was essentially where a lot of the famous autonomous vehicles were born. In fact, even Waymo comes from the origins of Waymo do trace itself back to DARPA, which was funded by the US government's defense sector. The last video, as you can see, was also involving the US Navy. So although we don't see direct uses of this in defense, the US government does. And it really trickles down into benefits for all of us civilians globally. Moving on, we'll now move to a more technical aspect of this presentation, where we'll be looking at, as in how you would look at ACC as an engineer. So till now we've been going over just like an overview of what ACC is, what CACC is, but now let's get to an engineering approach to how you would address, define, analyze ACC and CACC systems. So basically, the main system function of adaptive cruise control is to control vehicle speed adaptively based on a forward vehicle by using the information about range to forward vehicle, the motion of the host vehicle, which has the ACC, the one you are in, and recognize driver commands, right? So just a simple diagram that's there on the side, on the right. In the middle is your ACC controller. The inputs it's getting are the detection and ranging of the forward vehicle. Essentially, what the radar can do is track it laterally and longitudinally, see if it's an obstruction in your lane, and respond accordingly. And if it's not, then it can respond accordingly. There is also subject vehicle motion determination. So now this can be based on the driver or an upper level controller, which could be an autonomous controller. So what I mean by subject vehicle motion determination could be speed, could be lanes that you're in, could be lateral, could be lateral control like steering, whatever it may be. Then if there is a driver, then what are the driver commands coming in, and how is the driver responding, and basically send it out to the driver then. So what are the conditions for ACC? Like when you look at an ACC system, what are the conditions of the system? So essentially what we're looking at is individual stability. That is our primary goal when you talk about ACC. What does individual stability, how do you quantify it? So that's when the spacing error of the ACC vehicle converges to 0, when the target vehicle is moving with a constant velocity. This is, essentially an ideal condition. That's how we always start, right? In engineering, you set an ideal condition and you try to achieve it. Mathematically, how do I represent it? So mathematically, delta I, as you can see the equation on the right hand side, delta I is your spacing error. So what you want is xi minus 1 plus the change in this thing should be equal to 0. And when can you say that individual stability has been achieved? That's when your acceleration is 0 and your spacing is 0. Because if you're not accelerating, then you're maintaining a constant spacing, right? So that is your primary desire when it comes to designing an ACC controller. If we move up slightly, then you talk about string stability. So string stability of a string of ACC vehicles, we are essentially moving into CACC territory here. But what we were trying to do it only with the radar, right? So essentially what happens is in an equation here, we have xi and xi minus 1. It essentially keeps increasing to xi minus 1. Then you have an xi plus 1, xi plus 2, and so on and so forth. Here, it's basically just, like a state flow diagram for an ACC control architecture. What is the overall system, right? So here you can see first is the commander, which is the desired algorithm. Here, all your inputs are going in, right? Everything that we spoke about earlier. So the range, the R dot, which is basically the rate of change, then the velocity that the driver is set, the desired headway time, which is essentially the distance or the time you set with the lead vehicle, and the velocity of the vehicle that we are in. All of this essentially translates into something as simple as acceleration commands, which then go to the controller, the ACC controller, which then sends them to the engine or the braking system as required, and essentially that controls the vehicle. As you can see here, that what we get is the velocity looping back. That's our feedback in the system, just making sure we have to make sure that we are at the correct velocity at all times, and that controls our acceleration. If I was to model this as an upper and lower controller, basically your upper level controller determines the desired acceleration of the vehicle. Now, your upper level controller could either be the human driver, which determines the velocity and sets everything and then gives it to the ACC controller, or your upper level controller could also be your autonomous system, which is basically looking at the overall environment and telling the lower level controller, which is your ACC controller and your brake controller, what to do. So your upper level controller is a hybrid of either just the ACC system, it could be the driver, or it could be the autonomous controller. For most applications that you'll see, for non-autonomous applications, the upper controller is just the ACC system. So it's essentially just the radar and the ECU. It's calculating in real time based on the inputs that it's getting and just sending the desired acceleration to the lower controller. And the lower controller is essentially your mechatronic actuators, which is essentially sending a signal out to your mechatronic controllers to either accelerate, brake, or whatever it needs to do at that point of time. So essentially, the plant model, the controller that we have is the system input is your acceleration. So that's what I mean when I say x dot I, x double dot I is equal to u. Once you move into an actual real application, now this is the ideal application like I've discussed earlier. Once you move into the actual application, there is always a lag, right, between the request sent by the upper controller and the implementation, just the mechanical lag and the electronic lag that exists. So you can add a factor called tau, right? So when you do the Laplace transform, essentially what you get is the acceleration is equal to 1 plus tau s plus 1 by tau s plus 1 into the UI. That's the input that's being sent. Now, what are the different control strategies that I used? I'm going to discuss the two most common ones. There is constant distance control. You maintain a constant distance with the vehicle in front. This is regardless of anything, like no matter what the velocity is, you always maintain a constant distance. This is not suitable for autonomous applications because the spacing error keeps increasing, especially since you're trying to maintain a distance. Any error in the distance gets multiplied pretty quickly, so it's not desired. Even when Bosch says there's a constant distance being maintained in their video, it's actually a hybrid of distance and time. It's more time based because you would want your vehicle to be closer at lower speeds, faster, and greater distance at highway speeds. I mean, if you set a distance of say 3 car lengths at 80 kilometers per hour and you're in stop and go traffic, so imagine you come to a red light at the end of this traffic, you don't want to maintain 3 car lengths, right? Somebody's going to move in and cut you off, and then that's basically going to keep pushing you back. So constant distance control was one of the first ways people thought of ACC. It's not really used very often now. It's not the desired way. It's more a hybrid which is used. And the other strategy, which is more commonly used, which is actually preferred, is constant time gap. So basically, in constant time gap, the desired inter-vehicle spacing varies with velocity. So it's pretty simple to understand, right? So essentially, if you set like a 3-second distance on the highway, a 3-second distance at 80 kilometers per hour is a certain value. But when you go down to like city speeds, which is maybe 20 kilometers per hour, 30 kilometers per hour, it reduces proportionately. So you still maintain a safe distance, right? But you can be confident that nobody's going to get in between your vehicles, or there's too much space and you're wasting space in like a traffic jam. If all the cars are maintaining a 3-vehicle distance in a traffic jam, then your traffic jams would extend for like kilometers because there's so much wasted space in between. So how would we model? So this is something that I modeled on Skill-Lync. This is a pretty rudimentary ACC system that I modeled. It's again based on the same state flow that I showed you a few slides up, which is basically looking at the current speed, the front vehicle speed, and the current distance of the vehicle in front. And we feed all of that information into our adaptive cruise controller. And as you can see, the only output from our ACC block is vehicle requirement, acceleration requirement. Here it's being sent to the vehicle model just to translate, because obviously there are going to be losses and just the response time and everything. And again, that's sent back as velocity all the way back into our adaptive cruise controller. Again, this is almost exactly like the state flow I showed you earlier. In fact, it was modeled based on that. The thing we really need to analyze as engineers who are working on an ACC system is what lies within this ACC block. That's the crux of it. I mean, that's what separates Bosch from Continental from all the other manufacturers, and how OEMs implement it. This is what really matters, the contents of this block, how you handle these 3 signals. using these three signals is pretty straightforward. I mean, yeah, we know this is what you need, but what do you do with them? So again, this is the guts of that controller. I'm not sure if it's self-explanatory, but basically you get these signals and you analyze them based on what you want. So let's just follow the velocity, right? So essentially, you send the velocity from you're looking at the current speed of the vehicle. Here it goes up. There's a PID controller which is looking at the set speed. So essentially, it's trying to modulate your speed to make sure that you're close to this ACC set speed, and it's sending it to your vehicle acceleration control. It also comes in here with your front speed, and you're measuring the delta and you're sending it here, which then also measures it, compares it to the current distance, the safe time that you've set, and sends it to, again, different PID controllers within your algorithm, and essentially is giving you a constant requirement of acceleration based on the inputs that you're getting. I have a few graphs that we'll get to after this, where I've basically modeled the performance of this and seen how it reacts, how it behaves. So let's just look at those. I think that'll help you understand what this does and how you analyze it. So to analyze the performance of my ACC controller, what I did was I sent a target vehicle with the sine wave input, sine wave velocity input. So my lead vehicle is moving with the sine wave velocity, right? So if you look at the maroon line here, that's the current speed of the vehicle. The blue line is the front vehicle speed, right? And if the yellow line is what is set for a constant distance control. So as you can see, based on constant time gap, the response is a lot better. There's a lot less fluctuation. That's why constant time gap will probably feel better than constant distance gap in this one, because with constant distance, you're always one step behind, because you're always trying to estimate how much distance you need to maintain. And that always keeps you on the back foot. So as you notice, that's why you notice that there's always excess input when it comes to constant distance, but with constant time, it's a lot smoother. For current distance, again, if you notice here, the current distance is maintained very well for the constant time gap controller. The constant distance is always trying to see, again, as you notice, it's constantly lagging. So here you see it is following a sinusoidal pattern because of the constant movement of the front vehicle. This error can add up really quickly. So that's what we discussed earlier, that a constant distance gap is not suitable for ACC, because once more than one vehicle is added, that delta can add up really quickly. So if I was to add more than one vehicle here, you'd see that one of them, I mean, as you move on, so from vehicle 1 to vehicle 2, vehicle 2 to vehicle 3, it would really just keep exponentially increasing the error. And that would cause a lot of chaos in real world applications. Another maneuver we did was stop and go to see how it responds. For stop and go vehicle traffic, again, you can see that the current speed for this thing, what's it called? Here, the graphs are actually flipped. The blue is the current speed for the CTG, and purple is current speed for CDG. Again, you notice that the blue, the current time, constant time gap, tracks our lead vehicle a lot better than the constant distance does. If you look at the distance between the two vehicles, you can see that it's maintaining a constant distance at all time. That's what CDG does. So I guess there's not a lot of difference in this, but it's important to analyze both and see where the advantages are and what those advantages are, so that you can decide which one you want to implement. So for this project that I did, I essentially looked at the performance across a bunch of different maneuvers. It was not just this, there was emergency stopping. You can essentially, depending on how flexible your ACC controller is, you can input whatever you want and see how it behaves. That's one of the reasons why Skill-Lync and MATLAB is often used to model all of this. It just makes life a lot easier, and you're able to evaluate a lot of things really quickly once your controller is designed. So that's why all of this was done on MATLAB. So yeah, let's move on to CACC and the control architecture that you would use for a constant time gap design when you move to CACC. So essentially the control input is still the same. It's still your acceleration. The only change is that it now extends. It's not just for U1. It's U1 plus U2, U3, U4. It goes all the way down the chain. Model is basically showing, this image on the right shows you essentially what's going on. There's a radar, there's wireless communication, there's a bunch of other things going on. We've already discussed this, that the distance between the vehicles is proportional to their speeds. In case the speed is doubled, the offset distance is also doubled, right? Which is essentially how you would drive as a human. You always like to maintain like a constant time gap. Essentially, it's even recommended. So the recommended driving practice at 100 kilometers per hour is about 3 seconds between you and the vehicle in front to give you enough space to brake, right? it has massive implications when you get to individual and string stability. Some more equations I'm going to throw your way now. Basically, the headway to be maintained by the vehicle that we need to maintain. So if you go back to this previous diagram, the headway is basically the distance that you need to maintain between your vehicle and the vehicle in front. This can be represented by this equation. Right now, if you use this in the control equation, you will get the equation that I have at the bottom, which is the UI equation. Right, it looks very complicated, but there are pretty simple ways to derive it. I mean, once you start doing the mathematical representation from the beginning, I could show you all the equations, but unless we sit down and work through each step, it's going to get really complicated, and it really won't serve the purpose of helping introduce you to CACC, ACC, and the basics. So essentially, I've jumped to the last equation just to show you that it does take into account a lot of different factors, and it's not just based on the delta or just the speed of the vehicle. It actually does get quite intricate, and that's why CACC is a challenging engineering problem. So where are we today? Where are we today with ACC and CACC? So exploratory advanced research, again conducted by the FWHA, which the video we just looked at today, they are now outlining what CACC, how to define the scope of CACC, specifically how to join and leave a platoon. It's not possible for all the vehicles in traffic to be going at the same place, right? So it's important to define where you're joining and where you're leaving. So the standards for CACC have been defined and they're all in place. The challenge now is how to incorporate or accommodate a vehicle leaving. It's quite interesting. A lot of research papers out there. They're all in pretty simple language if you were to look for them online. Analyzing them is the challenge as engineers, and finding them. So yeah, that's what this is about, just to give you a good idea of what it is, to give you a good step to build up on once you read those papers, so you can actually analyze them from an engineering point of view. Then you've got cooperative following, which is basically CACC, but slightly more. So it's essentially not just a simple CACC, but you're smoothing the flow. So you're accommodating for a giant string of traffic, and it basically controls your traffic based on those inputs. And now, why would you want to learn about CACC? I mean, all of you, I'm sure some of you are looking for jobs, maybe in the future, maybe not today, but why would you want to be interested? Now, ACC and its various forms are used across the entire automotive industry. I mean, it's not just passenger car business, it's not just commercial, it's used across. There are a few companies who have the best equipment. So Bosch, Delphi, Continental, they have the best equipment when it comes to radars, when it comes to cameras, and even modules like complete ACC modules. But some OEMs, like especially all the new autonomous OEMs, they prefer to do it their own way. In commercial vehicle business, it's again the same way. So what a lot of manufacturers do is they buy equipment from Bosch, Delphi, Continental, install it in their vehicles, and design their own controllers. Because in today's day, the radar is smart enough to give you all the inputs that you need. So essentially, your front vehicle speed, your front vehicle distance, decel, all of that is being calculated in real time by the radar. All of that information is sent to your own ACC controller, and you can decide how you want it to react. But to get to that point where you can design it, essentially what you need is very good system knowledge. You need to understand, what goes into a lower level controller, what goes into a vehicle dynamics design, because it's. I mean, you can't accelerate and brake without understanding how the vehicle is designed. Because I mean, you are aiming for comfort. So deceleration limits, brake application, the way it's applied, all of that, to understand all of that in a fundamental way where you can design ACC controller which can be used by an OEM, you need very good system knowledge. And to implement all of that knowledge, you need a strong background in controls. You need to have a good grasp of controls and be able to understand how you convert all of those equations into an actual implemented system. So yeah, that's what you need. That's what ACC requires. That's what the industry requires from professionals who are interested in working on ACC. Again, it's not really a standalone vocation, but it's a very big part. In fact, a lot of my work is with ACC these days.